In this video, we will discuss about minimum number of removals to make mountain array. Given an integer array nums, return the minimum number of elements to remove to make nums a mountain array. So what they are saying is that in the input, we are given an integer array and we need to form a mountain from this array, right? After removing some of the numbers. Or if it is already a mountain array, then we do not have to remove any numbers. So now, what is a mountain array? What are the conditions for it? So the conditions are, first is that the array length should be at least 3, right? The array length should be at least 3. Now the second condition is that there must be some index I, which is not the first element and not the last element. It should be in the middle, and that is why we are saying that the length should be at least 3, right? That is the reason. So there should be some index I in between the first and the last element, such that all the elements to the left of this index are in strictly increasing order and all the elements to the right of it are strictly decreasing. If this condition holds, then this I is the peak element and this forms a mountain array. Okay. Now, you need to convert this array to a mountain array after doing minimum number of removals, right? And then whatever is the minimum number of removals that you are performing to convert this array into mountain array, that you need to return as your answer, right? So now, how can we do that? So now we don't know what will be the peak element of our mountain array, right? So what we can do is that what all possible numbers can be our peak element, that all we'll consider. For example, this one, like from here till here, all of these elements can be your peak elements, right? So we will check for all of these. So for example, we are considering 5 as a peak element. So we will see that before 5, what is the longest increasing subsequence that you are getting, and on the right hand side we'll find out what is the longest decreasing subsequence that we are getting, right? So what did I say? I said longest increasing subsequence, right? Now let's understand this, why we are saying this. Why is this longest? Because we want to perform minimum number of removals, right? Minimum number of removals. Then why increasing? Because to the left of peak element, the all elements should be in increasing order, right? Should be in strictly increasing order, right? That's why we are considering increasing. Then why subsequence? So first let's understand what is a subsequence. So a subsequent is nothing but some elements from your array which may or may not be contiguous while maintaining the relative order of the array. Meaning, one of the subsequence of this array can be, let's suppose I take 2, then I can take 5, and then let's suppose I took 2 again, and then 3. So basically we can take any element from this array. This is not mandatorily have to be contiguous. It can be contiguous or non-contiguous, right? So after 2, it's not necessary that we should take 1 only. We can take other elements also. But one thing that matters is that the relative order of the elements should be maintained. So for example, here 6 is coming after 5. So in your subsequence also, if you are considering them, then 6 should always come after 5, after 1, and after 2. It can never come before them, right? So that is a subsequence, right? So for finding out whether a particular number can be a peak element, we'll check what is the longest increasing subsequence to the left of it, because we want to perform minimum number of removals. All the elements should be strictly increasing and we can form a subsequence. And similarly, to the right of the peak, we know that the elements will be in strictly decreasing order, right? That's why instead of longest increasing subsequence, we'll search for longest decreasing subsequence, right? So that is what we are going to do. So we will make each element as a peak and we will find out the length of LIS. We will refer longest increasing subsequence as LIS and longest decreasing subsequence as LDS. Okay. For every element in our array other than the first and last element, we'll check what is the length of LIS to its left and what is the length of LDS to its right? And whatever number of elements you would have ignored from these two, that you can combine, right? So now our problem statement is that how do we identify the longest increasing subsequence or longest decreasing subsequence? So we will come to this part later, identifying the peak element and then checking the length of LIS and LDS and then calculating. So we will come to this point again. First, let's understand how do you identify the longest increasing subsequence for a particular array. Okay. So let's remove this. So now let's suppose this is the array and we need to find out the longest increasing subsequence of this array. So what you will do is that you will start with the first element, right? You will create a subsequence. You will start with the first element. So it will be 1. Next is 7. Now, should I write 7 here or should I create a new subsequence? Now we want longest increasing subsequence, right? So I will try to accommodate as many number as possible inside the same subsequence, right? So instead of creating a new subsequence with 7, I will keep 7 here. And also I can keep 7 after 1 because 7 is greater than 1. So it will maintain the increasing property, right? So I will write 7 here. Then can we take 8 here? Yes, because 8 is greater than 7. So we'll take 8 now. Now next is 4. Now can I write 4 here? If I'll write 4 here, it will disrupt the increasing order. So what we'll do is we'll create another subsequence and we'll take 4 there. But now since we want longest subsequence, so you can see before 4, we also have 1 present here, right? And we can take this one also, right? Because they will be increasing 1 and 4, right? So we'll take 1 and 4 here, right? Next we have 5. Can we write 5 here? No, because again it will disrupt the increasing order. Can we write 5 here? Yes, we can. So it will be 1, 4, 5. Next we have 6. Can we write 6 here? No. Can we write 6 here? Yes. So here we'll write 6. Then we have 9. So can we write 9 here? Yes. Can we write 9 here? Yes. So it will be 9, 9, right? So if you will see here that the length of this subsequence is 4 and the length of this subsequence is 5. Which is the longest? This one, right? Now although you have got that the length of the LIS of this array is 5, but how did you calculated it? You found out all the possible increasing subsequences that you could out of this array, right? And then you took the maximum length, right? But this will take a lot of time and it will also utilize a lot of space for saving all the subsequences, right? So we want some other approach to find out the length of the longest increasing subsequence of this array, right? So for that, what we can do is we will perform longest increasing subsequence using binary search. Okay, using binary search. This is what we'll do. So what we can do is that here we are creating multiple subsequences. So instead of creating multiple subsequences, we will try to utilize only one subsequences. And in that we will try to find the length of longest increasing subsequence, right? So what we'll do is, let's start from the starting again. So we'll take 1 here, right? Then next is 7. We can take 7 because 7 is greater than 1. Then we can take 8 because 8 is greater than 7. Then for 4, we cannot take 4 here because 4 is smaller than 8. Right. Now earlier what we were doing is we were creating a new subsequence and we were keeping 1 and 4 here. Now what I am saying is that instead of creating a new subsequence, you utilize this one only and try to accommodate 4 inside this subsequence. Right. Now tell me, ideally if 4 was present in this LIS, then where would it be present? After 1, right? Because 4 is greater than 1, right? So what we'll do is, in place of 7, in place of 7, we will write 4 because we know 4 will be greater than 1 and 4 will be lesser than 8. Because since 4 was lesser than 7, then 4 will always be lesser than 8 also, right? So that's why we kept 4 here. Now this is not a valid subsequence. Why? Because we have disrupted the relative order of our elements, right? Ideally in this subsequence also 4 should come after 8 always, right? This is the property of subsequence. But here we have disrupted that order. So this is not a valid subsequence. But since we are only concerned about the length of our longest subsequence, so the order of the elements does not matter to us, right? We are only considered with the length. That's why we are not focusing on the order of the elements. It's just that we are focusing that they are in increasing order. We are not focusing on the relative order, right? Now after this 4, when you come at 5, now where can be 5 inserted? Can it be inserted here? No, because 5 is smaller than 8. Now where can it be inserted? Here, right? Because 5 is greater than 4, right? Instead of 8, we will write 5. Now if you see here that although we left 7 and 8, in place of that we took 4 and 5, still our length is same, right? Still our length of LIS till now is the same. We didn't lose anything, right? Then next we have 6. So can 6 be taken here? Yes, it can be taken. Then next we have 9. So can 9 be taken? Yes, it can be taken. So now you will see that you have got the subsequence whose length is 5. And earlier we saw that the length of the LIS for this array was 5. And same we have got here, right? So basically we are only focusing upon finding out the length of longest increasing subsequence and we are not concerned with the relative order of our elements, right? So what we were doing here is that when we are creating this LIS, whenever we got any element, we compared it with the last element in our LIS, right? If our current element was greater than the last element of our LIS, then we took it, right? Because it was maintaining the increasing order. But when our element was smaller than the last element of our LIS, at that time what we did was, when you had this 4, your LIS was looking like this, 178, right? Now you wanted to insert 4 in this, but 4 couldn't be inserted here because it was smaller than 8. For finding out the suitable position of 4, we will be using binary search. So what you need is, you want to find the first element in this array which is greater than or equals to 4, right? In this array, 7 and 8 are greater than 4. Out of these, you want the first element which is greater than or equals to 4. So in this case, it will be 7, right? If we had 1, 4 and 8 here, and then we wanted to insert the next element as 4, then we would insert it in place of 4. So 4 would be overwritten with 4. So we want the first number which is greater than or equals to this number. That will give us the correct position of inserting 4, right? Now this index can either be searched using binary search, or another thing, in C++, we have a function named lower bound. So what this lower bound does is, it returns you an iterator pointing to the index where this particular element is present. So basically, you give that function your array and the element, and it will give you the iterator pointing to the index of the first element which is greater than or equals to this element, right? So whenever your current element is greater than the last element in your LIS, at that point of time you can insert it in the back. And if it is not, then you should find out the first element which is greater than or equals to the current element, and in place of that you should write your current number, right? If you will do that for the entire array, you will be able to get the length of longest increasing subsequence, right? So now that we know how to identify the length of LIS, let's come back to the point where we left our question. So now, what did I say? I said that we will consider each element as a peak element, right? And for every peak element, let's suppose this 5, I want what is the length of LIS on its left and what is the length of LDS on its right? Now you understood how to find out the length of longest LIS, right? Now how will you identify the length of longest decreasing subsequence, that is LDS? It's very simple. It's very simple. If let's suppose this 5 is the peak element, and out of this much array, that is 6, 2, 3, 1, you want to find out the length of longest decreasing subsequence. So can you reverse this array? If you reverse this array, you will get 1, 3, 2, 6, right? Now if you find out the longest increasing subsequence of this array, right, what it will be? It will be 1, 2, 6, right? You will find out this, right? Now I am saying, since we reversed our original array, we find out the longest increasing subsequence. Now if I reverse this longest increasing subsequence back, then I will be able to get the longest decreasing subsequence of this array. So if I reverse this, we will get 6, 2, 1. Now just look here. Can this be called as the longest decreasing subsequence of this array? Right. 6, 6, 2, 2, 1, 1, right? 3 we didn't include because 3 was greater than 2, right? So what we can do is, whatever function you will write for finding out the length of LIS, same you can utilize for LDS also. It's just that you will reverse your array, and whatever is the answer that you will get, you will reverse that also, right? Now we wanted to consider every element as a peak element, right? So then that means for every element, I want what is the length of LIS on its left and what is the length of LDS on its right? And what we just saw, that we were finding out the length of LIS for this entire array, right? If you apply the logic of LIS on this array, then what you will get? For this first element, your LIS will look something like this, right? So now tell me that at this very index, what is the length of your LIS? 1, right? Because we only have one element in our LIS, right? So what we'll do is, I'll create another array of the same size as my original array, and at every index, I will keep the length of LIS to that index, right? Meaning at this point 5, it will store what is the length of LIS till 5, starting from starting till 5, right? So at this point 2, the length was 1. So corresponding to 2, we will keep 1, right? Now comes 1. So now 1 cannot be inserted here, right? So you will find the lower bound for 1. What will be the lower bound for 1? 2, right? So in place of 2, 1 will be written, right? Now at this point, what is the length of your LIS? 1 only. So we'll keep 1 here. Next we have 1. Now 1 cannot be inserted here because these two are same. So you will find the lower bound. Lower bound will give you the first element that is greater than or equals to this element. This one is equals to this element. So in place of this one, another one will come. Right. Now at this point also the length is 1. So we will keep 1 here. Now we have 5. Can 5 be inserted here? Yes, because 5 is greater than 1. So we'll keep 5. Now at this point, the length has become 2. So we will keep 2 here. Next we have 6. 6 can be inserted here. So we will insert 6. Now the length has become 3. So corresponding to 6, we will store 3. Right? Then we have 2. 2 can be stored here? No. So we will find the lower bound. What will be the lower bound for 2? 5. Right? So in place of 5, we will get 2. Right? And the length remains the same, which is 3. Next we have 3. Can 3 be inserted here? No. Then what is the lower bound? 6. So in place of 6, we will get 3. Length remains the same as 3. Next we have 1. 1 cannot be inserted here. The lower bound for 1 will be this one itself. So this one will be replaced by another one and the length will remain 3. Right? So now this is one of the arrays which we have generated, and this array gives us the length of longest increasing subsequence up to index I from the start, right? Then that means if corresponding to this 5, 2 is stored, then that means from the starting till this 5, the length of LIS is 2, right? Similarly, so this we stored for LIS. Similarly, we will generate for LDS also. This is what you will get. So this will be your LIS lengths and this will be your LDS lengths. So now what all information do you have? This was your original numbers array. Then these are the lengths of LIS and these are the lengths of LDS. So for every element, you have these two information. So now let's suppose our peak element is 6, right? Now for 6, how many number of elements were present for the left? These many, which is 5 elements, right? And what is the length of LIS that you have got? That is 3. So 5 minus 3 is 2. Then that means we had to remove 2 elements from the left, right? Then if you see for the right, so for the right we had 4 elements, right? And what is the length of LDS that you are getting? That is 3. So 4 minus 3 is 1. So that means from the right you had to remove 1 element. On the left you had to remove 2 elements. So total 3 elements you had to remove, right? So for every possible peak element, you can find out that how many removals were done, right? Now out of all these removals, you can check that, okay, whichever is the minimum, that will be your answer, right? Now how to check that? How you will identify how many removals were performed? So if you see here, let's suppose my peak element is index I. Then that means in my nums array from 0 till I, the elements should be strictly increasing, right? How many elements will be present in this from 0 till I? It will be I plus 1 number of elements, right? Then for the right hand side, that is from ith index till n minus 1th index, where n is the length of your array. These elements should be strictly decreasing, right? Now in this, how many number of elements are present? N minus I elements, right? Then that means through this formula, I can find out how many numbers were originally present to the left and right of a particular peak, right? Then from this LIS length array, you can identify what is the length of LIS for this index I. So let's suppose that is L1. Then through this LDS, you can identify what is the length of LDS for this I. So let's suppose that is L2. So how many elements would have been removed from the left? Total were I plus 1 and we are left with L1. So the removed number of elements will be I plus 1 minus L1, right? And similarly for the right, it will be N minus I minus L2, right? So now these are the number of elements we have removed from the left. These are the number of elements we have removed from the right. Whatever it's their sum, that gives you the total number of elements you have to remove for considering this particular index as the peak of your mountain array, right? Now if I write these two expressions together, it will be, can this I and this I be cancelled because this one is positive and this one is negative. So these got cancelled. Now we are left with 1 minus L1 minus L and N. So can I write this expression like this? So this is the expression that will give you the number of removals. So for every element in your array, you can apply this formula, which will give you the number of removals. You can track the minimum number of removals that you have got, and at the end, you can return that minimum number of removals, right? Now, one more thing to be noticed here is that the first condition of our mountain array was that its length should be at least 3. So there will be one peak element I, and to the left of it there should be one element at least, and there should be one element towards the right at least. So if in case for any particular element I, your L1 or L2, meaning the length of LIS or the length of LDS is 0 for either of them, right? Then that means that won't be a valid mountain array, right? So this calculation you will perform only when L1 is greater than 1 and L2 is also greater than 1. So that are all the main points of our question. Now let's try to code this. I hope you got the gist of the problem. When you will code, you will be able to understand better. So first of all, we'll take the size of our nums vector inside n, right? Now we need to create a vector for storing the lengths of LIS, right? So we'll create a vector of type int and we'll name it LIS. Now in this, we will call our function which will return us all the lengths of LIS for every index, right? So what we'll do is, let's create a function which will return us a vector of type integer, right? Let's name it LIS length, right? Now what it will receive? It will receive our vector, right? Original vector. Let's name it V. Now inside this, we need two vectors, right? In one, we will store the LIS that we are creating, and in one, we will store the length of LIS up to the index I. So first, let's create a vector. Let's name it LIS, right? So initially it will store the first element of our vector, right? And then we can create another vector which we will return. So let's name it lisLength, and it will be of size equals to v dot size, and initially it will store 1 because there will always be at least one length present. Then we will start our iteration from I equals to 1 till the end, which is v dot size, and then we'll do I plus plus. Now inside this, what we need to do is, first we need to check whether this is greater than the last element of our LIS or not, right? So let's write if v of I is greater than what? Greater than LIS dot back. If it is, then in LIS, we can simply push V of I, right? And if it is not, then that means we need to find out the lower bound, right? So now we will apply the lower bound function. Now this lower bound function wants the starting and ending iterator of the vector in which we want to find the lower bound. So we'll do lis.begin, lis.end, and then we need to pass in the element for which we need to find the lower bound. So that will be v of I. Now this will return us an iterator pointing to that lower bound, right? We need its index. So for that, what we'll do minus lis.begin. By doing this, we will be able to get the index of that lower bound, right? And then at that index inside our LIS, we can simply update it to VI, right? And at every iteration of this I, you will also update your LIS length, right? So LIS length of I will be equals to what? The length of your LIS, right? So LIS dot size, right? And then at the end, you can return your LIS length, right? So now here we'll call this function. So we named it LIS length. This will receive your nums. So this will give you the lengths of all the LIS. Now you want the lengths of all the LDS. For that, what I told you that we will first reverse our nums, right? So we will reverse, we'll write nums dot begin, comma, nums dot end, right? Then what we'll do is, we'll call this function again. So this will give us LDS, right? We'll call this function LIS length again, and then it will receive nums, which is reversed. After you have got your LDS, you need to reverse this also, right? So we'll do reverse LDS dot begin, comma, LDS dot end. So now you have got your LIS and LDS. Now you will try to find out the minimum number of removals. So for that, let's create a variable removals, which will initially store int max. Then we'll start iterating in our vector. So it will start from 0 and it will go till n. Inside this, what we need to do is, we need to check. What we need to check here, that if LIS of I is greater than 1 and LDS of I is also greater than 1, right? Then in that case, we will update our removals. So removals will be equal to minimum of removals, comma, the formula that we had created. So the formula was n plus 1 minus L1. L1 was LIS of I, right? And then minus L2. L2 was LDS of I, right? And then in the end, you can simply return your removals. So let's run this now. So our test cases are accepted. Now let's submit this. So it got accepted. Thank you so much for watching. Please subscribe our channel.